Hello, and welcome to ACSL Computer Number Systems. To begin to understand number systems as they appear in ACSL, we're first going to understand what exactly number systems are. So when we count, or let's try to count some quantity. When we start to count something, we go from 0 to 1 to 2, 3, 4, 5, 6, 7, 8, and then up to 9. After 9, we go to 10. Now, what does this actually mean? Well, essentially, we're saying we have one quantity of 10 objects and zero quantity of one object. We only have digits from 0 to 9. There's no one character that represents 10 things. So to compensate for that, we'll say we have one group of 10 things and zero group of 1 things. Now for 99, for example, we're saying we have 9 groups of 10 and 9 groups of 1. If we wanted to go further, again, there's no character to represent 10 things. There's no single character to represent 10 things. So we're going to add a new digit to this number, and we're going to call it the 100ths place. So here we have one group of 100s, zero group of 10s, and zero group of 1s. Same thing. For a million, we have one group of 10 to the 6th, zero groups of 10 to the 5th, zero groups of 10 to the 4th, and so on and so forth. The observation here, that's pretty crucial, is that for each new digit we add, for each new place we add, what the group that it represents is an exponent of 10. So you can see we go from 1 to 10 to 100, which is 10 squared, to 10 cubed, to 10 to the 4th, to 10 to the 5th, to 10 to the 6th. So, as a quick side note, why do we use base 10? It's known that other cultures may have used other bases. For example, the Babylonians used base 12 and base 60 because 60 is very easy to divide and has a lot of factors. That's one of the reasons why clocks have 60 minutes and there's 12 hours, etc. And the Romans used a numbering system without one clear base. But the reason why we use base 10 is because, we have 10 fingers, so it's really easy to count and conceptualize making groupings of 10. So let's take a look here. We have 0, 1, 2, 3, and then 4. And then 0 in base 5, 1 in base 5, 2 in base 5, 3 in base 5, 4 in base 5. We're going to try and count in base 5. And as I mentioned, they only have 5 characters, 0 through 4. So when we get to this point, unlike base 10, or like base 10, we're going to do one group of 5 and 0 groups of 1s. So because in base 5 we don't have a character to represent the number 5, or the quantity 5, we're going to start making groupings of 5 things. So this 10 in base 5 is essentially the same quantity as 5 in base 10. 20 in base 5, for example, we'd have 2 groups of 5 and 0 groups of 1, so this would actually be 10 in base 10. Now let's say we had 413. We would have a 1's place, a 5's place, and a 25's place. And again, if we were to go to a million, you would notice that what these places represent are exponents of 5. We start at 5 to the 0s, which is 1, and then 5 to the 1, which is 5, then 5 squared, which is 25, and 5 cubed, 5 to the 4th, 5 to the 5th, 5 to the 6th, etc. So, a note on notation. So this quantity, because there's no base listed, you would assume is base 10. But here, this is the same quantity but with an 8 here. So now that there's an 8 here, you know this is base 8. And therefore this and this, these two numbers are different quantities because you have to assume that this one is base 10. Alright, so that's enough on number systems in general. Computers specifically, and this is what you'll see in ACSL, use 3 number systems: binary or base 2, octal or base 8, and hexadecimal or base 16. So let's take a look at some binary here. This would be a binary number that has 7 places, and we can see what each place represents. We have 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, etc. And so this first one would be the 1's place, this would be the 2's place, this would be the 4's place, 8's place, 16th place, 32's place, and 64th place. Now, let's do some counting. So 0, 0, 0, 0, 0, 0, 1 would just be 1. Now, if we add another 1 here, this would be one group of 2 and one group of 1, so this would be 3. Adding 1 here would make this 7 because we have 1, 4, 1, 2, and 1, 1. And so what is this, for example? This is 132 plus 1, 8 plus 1, 2 plus 1, 1. So this would be 43. So what about octal? Octal, very similar spiel, except again, the places are different. So instead of 2 to the 0, it's 8 to the 0, then 8 to the 1, then 8 squared, etc. So it's the 1's place, 2's place, 64's place, 512's place, and then, etc., etc., etc. And because it's at base 8, we have 8 characters, so we can use the numbers 0, 1, 2, 3, 4, 5, 6, and 7. Binary, you can only use 0 and 1. So a key trick here is that octal digits can be represented by 3 binary digits. So you can go from binary to octal pretty quickly. Hex digits can be represented by 4 binary digits. And speaking of hex, let's quickly discuss it. So obviously base 10, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And these are our 10 characters. But for hexadecimal, obviously we need single characters that represent larger numbers than base 10. So 10 in our base 10 would be A in base 16, 11 would be B, 12 would be C, 13 is D, 14 is E, and 15 is F. So 3E16, this would be, E is 14, so this would be 14 in the 1's place and 3 in the 16's place. And this ends up being 62 in base 10. So one other thing to know is that we can determine the decimal values of other bases by subbing each digit multiplied by its place value, as I alluded to earlier. And so what we have not yet covered is how to convert from decimal to other bases. So let's say we want 100 in base 10 to be in something base 8. So what you could do is do this manually. You would see what times 64, and you would divide it by 64 and then find the remainder and quotient. And you get 1 times 64 plus 36, and then for 36, you divide it by 8 to the power 1 and get the remainder and quotient, and you get 144. So the answer would be 144 base 8. So you need to figure out of how many groupings make up the decimal number. Or you could just do it this way. You could do 100 divided by 8, and you get the remainder of 4. And do this divided by 8, and get a remainder of 4, and then get a final answer, a final quotient of 1. So when you have the final quotient that's less than 8, you do 144, and you get 144 base 8. Thank you.